Well, today we're going to pick back up on drawing structures using line bond structures and looking at some deviants after that. Let's look at this structure. If we drew this structure here, could we draw out all the carbons and the hydrogens that are associated with that? Okay. Well, let me do that for us. We would have this structure here. Okay? So this N carbon is a CH3, then we got a peak for a CH2, but then note the valley should be another CH2, but that's bonded to an extra carbon, so we have what? 1, 2, 3 bonds to carbon, so I have 1 left over, so I got 1 hydrogen there. End of bond, give me 2 CH3s. Okay? So starting to see how this works a little bit. We're going to continue to do a bunch of these so that we make sure we have these down. Let's suppose we had a structure like that. You can see these start getting more and more complicated. But can we draw this out? If we do, we get a structure like this. Give you a chance to write that down. Okay, so see how we have CH3, CH2, and then bonded to this carbon. Note this carbon has 1, 2, 3, 4 bonds on it. So I have 0 left over, so there's no hydrogens on this carbon. Then I get the same thing on this side. And then this comes down for a CH, and then a CH3 and a CH3. Again, this carbon has 3 bonds, so I have 1 left over for a hydrogen. Okay? Hopefully this one came at you a little bit more easier. Okay, let's do another one. Sometimes we can have rings as molecules. Okay, if you note here, we got a ring of how many carbons? 1, 2, 3, 4, 5, 6. Okay, and if we were to draw it out, our atoms would show up like this. Okay, so CH2s all the way around until this carbon that has this CH3 on it. If I note 1, 2, 3 bonds, 1 left over for a hydrogen here. Okay, so we want to make sure that we can understand what these rings represent here. Okay? Your homework will give you lots of practice of drawing these things, but just want to introduce to you some models. Let's look at some others. Let's suppose we had something like this, and I wanted to draw this in a line bond structure. Okay? So I'll give you a minute to draw that down there. Okay? So if I were to draw this in a line bond structure, I have how many carbons across? 1, 2, 3, 4, 5. So let's draw those. Okay, so that gives you the backbone of the molecule. And now I have an important rule. Anything that is not a carbon, I have to draw that atom. Okay, so the chlorine is on this second carbon. And I got a fluorine and an OH on that carbon. Okay, so I have to draw those in. Note I drew the chlorine on the top. I could have also pointed it down. Okay, what we tend to do is if I'm on a peak and I have an extra bond to a group, I want to draw that bond going up. If the group was on a valley carbon, I would draw that bond going down. Okay? Let's look at another example. Something like this. Here I have a ring structure with an oxygen in there. Okay. So if I were to redraw that, I would have something like that. Okay. Where again I have to show the non-carbon atoms. Okay. So maybe you can begin to see as I draw rings using the line bond structures, it's a little bit better than trying to draw these clumsy structures, isn't it? And it looks a lot more neater, doesn't it? But you've got to remember what each of these corners represent in the molecule. Okay? So we're going to use line bond structures a lot, so you need to get these down very quickly. You know, the importance of them, if I were to draw a molecule like this here, okay, you don't need to draw that, but note that I drew that in a matter of seconds. If I were to draw out the full Lewis structure showing all the atoms, carbon and hydrogen, that would probably take a couple of minutes to draw that. Okay? So this is the utility of doing such things. Okay? It makes it a lot easier to draw. You know, even if I have double bonds, I can show those in the molecule. Okay, so you should know what those represent. Okay, so if I have a double bond, that counts as a bond. So this is a CH3, This carbon, I've used 1, 2, 3 bonds, so I have 1 left over for a hydrogen. Same thing here, and then a CH3 over there. Okay? So whether I have a double bond or a triple bond, those still count. Okay? And so I still have to subtract from 4 to see how many hydrogens I have left in the molecule. Let's look at something else. Let's look at this molecule. Okay. I'm not going to be worried about the line bond structure, but there's another way I could draw this showing the atoms. Where I can shrink wrap by use of the parentheses. Okay? So if you look at this CH, it has 2 CH3s on it. Well, I can show that in a condensed manner by putting them in parentheses and 2, showing that these are 2 of them attached to that previous carbon. Okay? So the use of parentheses is used a lot in drawing structures. Okay. Similar, if you had a molecule like this, where if you look, you have a long string of CH2s. In fact, we have 5 of them. So again, we could use parentheses to show that. And so redraw the molecule like that to show I have 5 CH2s connected in a row between these 2 CH3s. Okay? So this gives us an introduction to drawing molecules. Make sure that you can handle drawing them. Okay? Whether it's parentheses or line bond structures and so on. Let's look at one last one here. Suppose I gave you a molecule like this. Again, you can see these molecules can get very complex. Okay? And I asked you to translate that to show all the atoms. Okay, can we do that? So these 4 carbons here would each be what? CHs, right? Because they've used 3 bonds each. So there would be the structure showing all of these atoms. Okay? So again, you want to make sure you can handle these things. Okay? And again, as you're trying to draw this, I think you saw that it was easier to draw this thing than to draw this clumsy structure here. Okay? So make sure you get on the homework problems in your book. Problem 1-10, problem 1-9 are good problems to make sure you can handle there. Okay, well, the last part of this chapter deals with a topic that's basically all to itself, and yet it is a very important topic for the whole sake of organic chemistry, okay? And so we want to dive into it. It's a topic that we've covered in general chemistry, especially in part 2 of it, okay? But it's one that we really need to review to make sure we're all on the same page. Okay? And that is the topic of acid-base chemistry. Acid-base chemistry. Okay? So let's spend a good amount of time getting our hands around this topic. Okay? Let's first of all give some formal definitions as to what makes something an acid and what makes something a base. Okay? Let's first of all look at the definition of a base. How do I know if something can act as a base? A very easy definition. Is that it must have a lone pair of electrons. It must have a lone pair of electrons. Okay? If something is to be an acid, then it must be electron deprived of some type. It must be electron deprived. Okay? So one of these things is full of electrons, and the other thing is electron deprived. So you can see how these two might react with each other. Let's make the base a capital B and the acid a capital A. Okay? If the base was a capital B, I need to include some lone pair with it. Okay? And if the acid is electron deprived, I might think it has some kind of positive charge with it. Here I'm drawing a full positive charge, but it could also have a partial positive charge as well. So how would these two react? Well, we could use an arrow to show this reaction. Okay? This is a very important arrow that is sometimes called the mechanism. Okay? So what a mechanism does is it shows electron movement. Okay? So make a note of it. When I show the mechanism, the arrow always starts at the base and goes toward the acid. It doesn't go the other way. Okay? You can think of it like the base is the quarterback in a football game. He has the football. And the acid is the receiver wanting to receive the football. Why doesn't the receiver throw back to the quarterback? Because the receiver doesn't have the football. Pretty simple, isn't it? Same thing here. The acid doesn't have the electrons to throw back. So if we draw the result of this reaction, we would end up getting something like this, where a bond is then established between the base and the acid. And that bond was lone pair of electrons on the base. So these electrons went from being non-bonding or a lone pair to becoming bonding between A and B. And so here we've made a molecule between these two groups. Okay? So make sure you understand the mechanism of how acids and bases react with each other. Okay? All right, well, let's look at some real molecules acting as acid and base. And let's start putting this together. Let's, for example, take OH minus and react with HCl. Okay. You probably recall from general chemistry that HCl is an acid. Why is that? It's because of this strong dipole moment between hydrogen and chlorine to give these partial charges. So this thing here will be the base, and that will be the acid. You can see I made the base very obvious with these lone pair and even with a negative charge. So if I see a negative charge, it's also going to be a very big tip-off that that will be the base. So how will these things react? Well, I'll choose one of the lone pair to attack the delta plus hydrogen. And note, these electrons are going to leave with the chlorine. Okay? You can imagine that the chlorine is pulling very strongly on this hydrogen. And if it's pulling, then it would like to fully let go if possible. So when the oxygen connects with this hydrogen, then the chlorine can let go because that hydrogen has bonded with something else. Okay? So the chlorine's dying to go away, and now since something else has initiated the attack, it can go away. And so what we end up with is this here, where now a molecule of water forms and chlorine has left as Cl minus. Note that we've kept charge distribution the same, negative over here, negative over here. Okay? Remember that we gave these things names. Since this oxygen gained a hydrogen, it becomes the conjugate acid. Okay? So the base always gives the conjugate acid, and the acid always gives this, which is what? The conjugate base. Okay? So you want to make sure that you can label acid and bases and conjugate acids and conjugate bases. Okay? Let's do another example. Here we have NH2 minus reacting with water. Note I have lone pair here and lone pair here. Which one's going to act as the base? Well, here I'll choose the one with the negative charge. So we have a dipole moment. You see the utility of drawing those partial positive charges that we learned earlier? So the nitrogen can attack and the oxygen can leave. The oxygen was pulling, now it can fully let go. So the nitrogen has gained a hydrogen. And the oxygen has gained a lone pair. So these bonding electrons now become a lone pair, and so the oxygen has gained a negative charge. Okay? So if we label once again, we get this labeling here where the base gains a hydrogen, so it becomes the conjugate acid, and the acid has lost a hydrogen, so it becomes the conjugate base. Okay? Okay. Let's look at one more of these things. Let's look at F minus reacting here. Here is the hydronium ion. Note that oxygen has a positive charge. When I have oxygen with a positive charge, it makes oxygen more electronegative. Okay? Because oxygen doesn't like to have a positive charge. And so it's really going to be pulling on these bonding electrons. It's going to pull them very, very much now. So this hydrogen is begging to be let go. And so the fluorine can easily attack to give us these two here as a result. So the fluorine has gained the hydrogen and oxygen has gained the lone pair. So now oxygen comes back to neutral where it's very happy. Note the charge balance, these cancel out, and there's neutrality over here for both of these. So that would be your base, conjugate acid, acid, conjugate base. Okay? Okay, well, let's look at another topic with acid-base chemistry. Again, make sure you can draw these mechanisms. You'll see as we get into later chemistry of organic that you'll see that a lot of organic chemistry is simply acid-base chemistry. Well, let's look at another topic here. This is the topic of pKa. pKa. Okay. So the pKa is a way to measure acid strength. It's a way to measure the acid strength. Okay? And pKa values can range over a pretty large spectrum here. They can range anywhere from -10 all the way up to as high as 50. Okay? What do these values mean? If the larger the pKa value, okay, this means that it's a weak acid. Okay? Versus if I have a very small pKa, it means that I have a strong acid. Okay? And there's some pKa values given in the chart on page 26, just to give you some ideas. HCl equals -7. Okay. H3O plus is -1. Water is a lot higher at around 16. When I get up to things like ammonia, its acid strength is very, very weak at a pKa of 33. Okay? So pKa's can be measured, and they can give you a wide variety of numbers based on how strong that acid is. Okay? So how can we use pKa's to our advantage? Let's take a look here. Okay. Let's suppose I wanted to look at HCl and water. Okay. If I were to take HCl and break it down to its conjugate acid and its conjugate base, we would get these two here. If I were to break down water to its conjugate acid, giving off H+, and it would leave behind OH- to give us something like that. Remember the pKa's of these. HCl at -7, and water was at about 16. Okay? So here, this is a much stronger acid. HCl is. Okay? Well, you might say, big deal, you just told us that. Well, here's the big deal, and that I can come over here and look at the conjugate bases. Okay? If this acid is strong, remember from general chemistry, it's always the opposite of the base. that would mean Cl minus would be a weaker base than OH minus. Okay? So OH minus will be a much stronger base than Cl minus. Okay? You see how we can use pKa's to predict that. Okay? So a weak base always comes from strong acid. Okay? A weak base always comes from a strong acid. You see, so how could I have predicted that this was a weaker base than this by using the pKa values? Since I knew this was a stronger acid than this, then I know that its base, its conjugate base, will be weaker than that one. You see how that works? That's a very important fact to remember. Okay? Let's look at some other comparisons. Okay, suppose I wanted to compare these two bases. Okay, I want to figure out which was the stronger base. Okay. Well, they can both act as bases, having the negative charge in their lone pair. But how can I figure out which is the stronger one? I have to go back and look at their acids. So this acid, add a hydrogen. And for this to be an acid, I would add a hydrogen here. I would then go and do what? Look up the pKa's of both of these acids. The pKa of HCN is 9. And the pKa of HF is 3. Okay? So now what do we do? Well, that means HF is what? A weaker or a stronger acid right? Because it has a smaller pKa value. So what does it say about its base? That means it's a weaker base. Okay, see how you can work backwards there. Okay, so Cn minus would be a stronger base than F minus. Okay, so that's how we can use pKa's to help us, not only to identify the strength of an acid, but also the strength of a base. And we'll be using that later on in our chemistry of organic molecules as well. All right, well, let's go ahead and stop here, and we'll continue next time.